So Isaac Newton is really the father of classical physics in many ways, one of the geniuses of his time. And he was the first to realize how objects moved with respect to the forces applied to those objects. It was thought before Newton that objects' natural state was to be at rest, because when you moved something, like a boulder rolling downhill, or an arrow flying through the air, it seemed like eventually those things stopped. That you needed to apply a constant force in order to keep something moving. Think about pushing a car that's out of gas. Once you push the car up to a certain speed, even on a flat road, you still have to apply a force to keep it moving at that speed. It wasn't until Newton, and actually Galileo slightly before him, but Newton formalized it, that they realized that the natural state of an object was actually only at rest if that object was initially at rest. Objects in motion want to stay in motion. The thing that stops them are external forces. In the case of an arrow, a little bit of air resistance and of course eventually hitting the earth. In the case of pushing a car, even in car in neutral, friction are external forces acting on those objects. If you look at an object with very little friction, like a ball rolling down a hill, a steel ball rolling down a flat metal sheet, if the ball is rolled at a speed uphill, the ball slows. If that ball is placed on the end of a sheet that's going downhill, the ball accelerates. So Galileo was the first to really postulate if the sheet is perfectly flat and a ball is rolled, that ball will roll forever. Now, of course, there's still a little bit of friction in that situation, and we'll talk about friction later on in this chapter, in this unit. However, this was the breakthrough. So Newton came up with his famous 3 laws of motion and his famous law of gravity, which we'll talk about a bit later. So in this unit, though, we're going to focus on his 3 laws of motion. And the first law of motion, Newton basically states in words, an object at rest will remain at rest, and a body in motion or an object in motion will remain in motion in the same direction unless acted on by a net external force. What does that mean? Well, in other words, a net external force is required to accelerate an object. If you want to accelerate an object, if you want to change that object's velocity, which means, remember, velocity is a vector. So changing an object's speed is an acceleration, and changing an object's direction of motion is an acceleration. To get that acceleration, you need a force, a net external force. And what do I mean by external force? Well, you have to have an external force. Internal forces don't work. No matter how hard I try, if I grab my shoelaces right now and pull up, I'm not going to lift myself off the ground, no matter how strong I am. That's an internal force. I'm pulling on me. That doesn't work. But someone could come by and lift me up. An external force can be applied to change my motion. And by net external force, I mean that the forces have to not balance. Right now, I'm being acted on by an external force. Gravity is pulling me down. Earth's gravity is relentless. Every morning when you wake up, it's there. Every evening when you go to bed, it's there. You will never experience a moment in your life that the Earth is not pulling on you gravitationally. It's always pulling on you. However, it's balanced right now for me by the fact that the floor is pushing up on me the same amount. And we'll talk about that in a bit. So there's no net force acting on me right now. The force is balanced. Think of it like a tug of war. You have a flag hanging from the middle of a long rope, and you have 2 equal teams of equal strength, pulling as hard as they can on either side. One team pulling to your right, the other team pulling to your left. They're equal in magnitude. They have the same strength, the same force of tension on that rope. They're in opposite directions, so the net force, when you add those 2 vectors together, they're equal and opposite, you end up getting 0 net force. And the flag just stays there, not accelerating. Alternatively, if both teams drop the rope at the same time, and it's just laying on the ground, Now there's no force to the right, there's no force to the left, and the rope is still just sitting there. If you want an object to accelerate, there has to be a net external force. In my tug-of-war example, one team has to be stronger than the other for that flag to move, for that motion to change. So we use these free body diagrams we talked about in the last video to identify the external forces. If those external forces don't balance, if the net external force is not zero, then that object will accelerate. Likewise, if the object is not accelerating, notice I didn't say not moving, although an object that's not moving has zero acceleration. An object traveling in a straight line at constant speed also has no acceleration. If an object has no acceleration on it, the net forces on that object have to be zero. Have to be zero. Like for me, I am not accelerating right now. I'm not accelerating downward or upward. I'm not accelerating to the left or the right. The net forces on me have to be equal to zero. So one way of thinking about Newton's first law, you can rewrite this basically, that the net force is proportional to the acceleration experienced. There's a little proportionality there because this is Newton's first law. It doesn't have an exact equation for the first law. It just says that net forces and accelerations are related. You cannot have one without the other. We will actually turn this into an equation in the next video, but before we do that, we have to talk about how these things are related. The resistance of an object to acceleration due to a force is what's called inertial mass, or just mass. The mass of an object is the property of that object to resist changes in motion. And all of you probably have an intuitive understanding of this, right? If you're driving with your friends to a concert and both of them take multiple cars and both of them run out of gas, which one are you more likely to want to push? The small little Mercedes for two-seater car, or the giant conversion van that your friends bring? Right? The smaller mass object is easier to push around. It's easier to push a less massive car than a more massive car. A car is easier to push than a semi. This inertial mass property is the property that resists changes in motion. Not just changes in motion to speed something up, but also to slow it down. Right? A school bus is harder to get started moving than a car. And once it's moving, it's harder to stop than a car is. A runaway school bus is a lot more dangerous than a runaway car is because it has more mass. So when you talk about changing the motion of an object, changing the motion of an object depends on that object's mass. Now, mass you could think of as the amount of stuff something has, the amount of matter something has. Unlike weight, mass does not change with location. So the astronauts that walked on the surface of the moon had less weight because the moon is not as large as the Earth and does not pull as strong gravitationally on the astronauts as the Earth does. But the astronauts' mass doesn't change. So weight loss programs aren't really weight loss programs, they're mass loss programs. You want to lose mass, right? You exercise, you diet to lose mass. Or if you really exercise and you eat a lot of calories and lift weights, you want to gain muscle mass. At least that term is used appropriately. So mass and weight are not the same thing. Weight is a force. And your book describes it as the force of gravity pulling down on you. We'll talk about that in a moment. Mass is the amount of stuff you're made up of. It turns out that these are related. The more mass you have, the more weight you have on the Earth, but they are not the same thing. So when you measure your weight in pounds, how many pounds you have, that you're literally measuring how strong is Earth's gravitational pull on you. Your weight changes depending on the situation. If you go up in altitude or down in altitude, your weight changes slightly because you're closer or further to the Earth. If you go to the moon, your weight will be significantly less, about 1/6 of that on Earth. But your mass doesn't change. Unless you diet or cut off a limb, your mass is going to be the same. Mass, remember, is measured in kilograms. That is a mass. Weight will be measured in pounds, which is a force, or newtons, which is a force.